Let's talk more about linear data. We're going to talk about how we measure how good a line is to represent our data. And the way we do that is we talk about correlation. A scatter plot, we look at the strength, the direction, and the form of the relationship between two quantitative variables. Well, that's fine, but we want to talk about a lot of times how good of a job a line will do to fitting that data. When we look at the data, a lot of things are linear in nature, but some things are better than others. It says here, unfortunately, our eyes don't do a good job of telling us how strong the linear relationship is. So what we do is we look at this thing called correlation. Our definition, we call correlation R, we use that abbreviation. It measures the strength of the linear relationship between two quantitative variables. So this is only for linear relationships. R is always a number between -1 and 1. If R is positive, that means there's a positive correlation. If R is less than 0, we have negative association. That would be the slope of the data. R values near 0 represent a very weak linear relationship. There's almost no linear trend to that data. As we get closer towards -1 or 1, the strength of our correlation is getting stronger. We are getting to more and more of a linear relationship. If R is ever +1 or -1, that means that we have a perfectly linear relationship, meaning all of those data points fall exactly on a straight line. So here are some examples. The top left one, the correlation is 0. That really doesn't follow a linear trend. If you look at these other ones, especially the bottom row, those have very strong, they look like they're following a line. These top ones have slight linear correlation. We could draw a line going this way. Doesn't do a real good job, but that's why the correlation is only -0.3. This one would have positive correlation. It's sloping upwards, not very spread out, or it is very spread out. It's not a very strong correlation still. As we get into the bottom row, these are looking more and more like lines. -0.7 there, +0.9, -0.99. So you can hopefully see that as this data gets bunched closer and closer and closer to an actual line, this correlation gets closer to +1 or -1. So how do we find the correlation? What's the formula for calculating R? Most of the time, we're going to use our calculator for this, but it's useful to see where it's coming from. So if we have data on two variables, x and y, for n individuals, the values for the first individual are x1, y1. That's the ordered pair for that person. The second individual are x2, y2, another ordered pair. So we have all these ordered pairs for these individual people or individual things. The means and standard deviations, we need to consider those in calculating this. X bar, that would be x with a line on top of it, and sx, and y bar and sy for the y values. The way we calculate our correlation between x and y is using this formula. 1 over n minus 1 times the difference of the x's multiplied by the y's divided by their standard deviation. So this is our formula. 1 over n minus 1 times the sum of our data value minus the mean over the standard deviation times our y data value minus the mean divided by the standard deviation. These are kind of like z-scores. So z-score of the x's, z-score of the y's, adding them up and then doing 1 divided by n minus 1. This sort of almost looks like a blend between the z-score formula that we've seen and actually the standard deviation formula, which tells us how spread out things are. And that's really what the correlation is measuring. So, some facts about correlation. Correlation does not make any distinction between explanatory and response variables. Remember, we're multiplying the x's and the y's together. And it doesn't matter what order we multiply things in, so we have no way to tell what's x, what's y. R doesn't change when we change the units of measurement for x, y, or both. The strength of the correlation will remain the same. The correlation coefficient R itself has no unit of measurement. If x and y are both measured in feet, R just doesn't have anything. R does not have units. And some misconceptions and some cautions: if you're going to talk about correlation, both variables must be quantitative. Correlation cannot be used to talk about the strength of a curved relationship between variables, no matter how strong the relationship is. Correlation is only for linear relationships. And correlation isn't resistant, meaning that R is going to be strongly affected by a few outlying observations. Remember, we're dealing with the mean in its calculation. Mean is one of those non-resistant quantities. So if we throw some outliers in, it's going to change our correlation quite a bit. And correlation is not just a one-stop shop for summarizing two-variable data. So I'm going to throw some graphs at you here. I want you to pause the video and think about what the correlation value R is going to be and interpret it in the context of the problem. So I'm going to flip through all four of these, then I'll go back and talk about each one, and then pause in between and write down what you think. So here's our first one. There's our second one. Third one. And fourth one. So let's start here. I would say that this data has a correlation coefficient pretty close to 0, because there is no real trend to this data. And what that means in terms of the quantity, or in terms of the interpretation, last year's percent and this year's percent return, I'm talking taxes here. This year I got 0% back. Last year maybe I got 0% back, maybe I got 60% back. One doesn't relate to the other. There is no correlation between last year's percent return on your taxes and this year's percent return. This one, I would say the correlation coefficient is probably somewhere in the neighborhood of 0.2 positive. We sort of have an upward trend going this way. And what it means to interpret that is that the healing rate of limb 1, as that gets higher, the healing rate of limb 2 will also get higher. And that should make sense. If you heal well on the left side of your body, you probably heal well on the right side of your body too. This one, again, positive correlation. I'd say maybe around positive 0.5. We've got a linear relationship going like this. Notice there is probably an outlier up here. And what that means is that as the number of storms predicted goes up, the number of storms observed also goes up. That should sort of make sense, that if we're predicting more storms, we'll probably see more storms. And finally, this one, I would say the correlation here is probably somewhere in the neighborhoods of 0.85-ish. It's a pretty strong positive correlation. And what this is telling us is that as the number of boats registered in Florida increases, so do the number of manatees killed by boats. So there's our practice dealing with correlation coefficient. In your practice problems, you're probably going to need to calculate some by hand, and you're going to look at how to do this in your graphing calculator. That's all for today. Stay tuned for more on correlation.